Hi, today we are going to look at the most important master thesis of the 20th century. It was not mine, but it was Claude Shannon's. We will go through it and we will see how he developed the method for using electronics to make a calculating machine. It is also an amusing fact that the most important he found out is hidden on one of the last pages of his master thesis. We all have to thank Claude Shannon for starting the digital race. So how do you find Claude Shannon's master thesis? Well, it's just to search for it on the internet. We just write Claude Shannon master thesis and PDF, and then you come to the MIT where he used to work. Here you find it, a symbolic analysis of relay and switching circuits. Here it comes. And then you can just go here, click and download it. Here it is, written in Courier font, a symbolic analysis of relay and switching circuits by Claude Elwood Shannon, University of Michigan in 1936. It's Master of Science at the Massachusetts Institute of Technology in 1914. Okay, here is the table of contents, introduction, types of problems. He was looking at switches and relays, series and parallel two-terminal circuits, multi-terminal and non-serial parallel networks, and synthesis of networks, illustrative examples. And the one we are going to look through in great detail is an adder to the base of 2 on page 59. And this is the most important that came out of Claude Shannon's master thesis, and also that he used Boolean logic to make electronic calculators. And then he has some references. And also he thanks his professor. And then he are talking about the types of problems. He is into relays, but we are looking to using what he found out when he was studying relays. Now we have jumped to page 7 and looking at fundamental definitions and postulates. Here are some text. We will just skim through that and go to some drawings. And here you see Shannon has drawn some circuits here with some switches. This is XAB switch. And here are 2 switches in series, and here are 2 switches in parallel. And when they are in series, he calls it X plus Y in this manner. And when they are in parallel, he is X multiplied YY. And then he has some postulates. 0 times 0 is 0. A closed circuit in parallel with a closed circuit is a closed circuit. And then he has 1 plus 1 is equal to 1. An open circuit in series with an open circuit is an open circuit. And then he has other definitions as well. And we see that this looks like Boolean algebra to us. For some odd reason, Claude Shannon chooses to use 0 where we use 1 and multiplication where we use plus. But apart from that, it's very similar to the way we treat our problems today. Yeah, and then he says that this is sufficient to deal with any kind of problems with these switches. And then there are some theorems that comes with this, and this is Boolean algebra. Yeah, and here you have some more thing. And then he also says that this is very analog with the calculus of propositions, which is Boolean algebra. Here's George Boole, and he's telling us that. We have already seen it. And then he digs a little deeper into that. We will not go through that. And here De Morgan turns up, that we also have the pleasure of using. And then he have this truth table. It comes here with the function equals, this function here equals something. And he is talking about Taylor series. I've never seen that, but anyway. Here are the analogs between calculus of proposition and this symbolic relay analysis that he has been doing. Now we have jumped to page 17, and here Claude Shannon gives us some more useful theorems. It's just more Boolean algebra. And then he shows an example of how to simplify circuits. And here we have a circuit with some switches here, like this. And we see that in order to have something going from A to B, W has to be closed, and then this must be open. So then we have a series here of W, X, Y. And you see, since this needs to be open, this part here will never give us anything. And in order for this part to give us something, set must be closed. And X is already closed in order to go through it here. So here it says that just set must be closed. Also here, Y is already closed. And in order to get something through, set bar must be closed. So this happens when this is open. And also here, to get something here, V must be closed. And in order to get something here, S dashed must be closed. So this simplifies to this here. We have this series here, and we have this parallel where we have when set is closed and when set is open, then S bar has to be closed or V to be closed. So this was a simplification of the circuit. And we turn our attention to page 21, where Claude Shannon shows us a general control circuit. It is like this. It has a positive side here and a negative side here. Here is a general circuit controlling relays X1 to Xn. He is also saying that these could be relays or any other electronic controlled devices such as lamp, etc. Now we have taken a large jump to page 45. On the previous pages, Claude Shannon looked at various forms of networks. We are going to just look at this way of building up a network. And contrary to Claude, we will say that when things are going up, this here is closed. And when we are on the same level, then it's open. And here you see that we have a circuit that represents S32. 3 means the number of levels we have up here, and 2 is where we are taking out the signal. And you see that there is a lot of different ways to come to number 2. Is either closed, close, open, or closed, open, closed, or we can come to it also by open, closed, closed. This can be simplified because there are things we don't need. We just need the things that can make us come to the position number 2. And these are the 3 possibilities: closed, close, open, closed, open, closed, or closed, open, open. Claude Shannon also shows us how we can simplify circuits by shifting levels down. We have this function S6 with 0, 3, and 6, which is desired. Instead of going up to level 6, we just shift it down. And here you see if you have, for instance, level 5 here and level 2. Level 2 is by going up here, and you get also level 5 going up here, going up here, going up here, going up here, going up here. That is 1, 2, 3, 4, 5. And this level that we want to take out is either having 0 going in straight line here, or having 3 by going 1, 2, 3 and out here. And we can have 3 also by going up here, up here, up here, and out here. And also here, up here, up here, up here, and out. And the 6 we get from going up here, and then we are going up here, up here, up here, and up here. That, if you count, is 1, 2, 3, 4, 5, 6. And then we can take all of them, 0, 3, and 6 out here on B. As I have already mentioned, Claude Shannon used the opposite signs than we have used. If is, of course, the same, that is equal, but or is a multiplication sign, and a plus is and. And here he has also shown that we can use it in reverse, meaning that multiplication is and plus is or. That depends on how you define the switch positions. At last, after 12 minutes of reading Shannon's master thesis, we come to what we are looking for: an electric adder to the base of 2, a binary adder. A circuit is to be designed that will automatically add 2 numbers using only relays and switches. Although any numbering base could be used, the circuit is greatly simplified by using the scale of 2. That was what I call a good observation. Each digit is thus either 0 or 1. The number whose digits is in the order are AK, AK minus 1, AK minus 2, ... to A2, A1, and A0, and has the value of the sum of j to 0 to k, aj2 to the times j. Let the 2 numbers which are to be added be represented by a series of switches ak down to a0, representing the various digits of one of the numbers, and bk to b0, the digits of the other number. The sum will be represented by the positions of a set of relays sk plus 1 down to s0. The number which is carried to the jth column from the jth minus 1 column will be represented by the relay gj. If the value of any digit is 0, the corresponding relay or switch will be taken to be in the position of what Claude calls 0 hindrance, if 1, in the position where the hindrance is 1. The actual addition is shown below. So then we have to look at it. Well, we've seen it before. We take adding 2 the A0 and B0. It adds to S0. If there is any carry from that, it goes to C1 plus A1 to B1 and it becomes S1. And if that has a carry, it goes further down the line and we end up with CK plus 1, which is the number we are looking for, is here. This is the number that we are looking for. It's the sum of these 2 numbers. We shall start with calculating the least significant bit. We have it here, is S0. That we get when we have either A0 equal to 1 and B0 dash equal to 0, or if we have A0 dash that equal to 0 and B0 equal to 1, and this function is the XOR function between A0 and B0. And the carry C1 we get if both A0 and B0 are 1. That means we have an AND function here between A0 and B0. To calculate the jth bit Sj, we need to take care of AJ, BJ, and also carry. And we get the Sj if we have one of these equal to 1 or 3 of them equal to 1. And we have a carry for the next g plus 1 if this function gives us 2 bits equal to 1 or 3 bits equal to 1. That means AG, BG, CG, 2 of them are equal to 1 or all 3 of them are equal to 1. Now we are going to look at how Claude Shannon made his digital computer. Here on the right-hand side, we have the circuit for the least significant bit. We have A0 and B0 that are going to be added together. If A0 is equal to 0 and B0 is equal to 1, then we get something out on S0. And if A0 is equal to 1 and B0 is equal to 0, we also get something out on S0. And you see that either having 0, 1 or 1, 0 give us something, and that is the XOR function between A0 and B0. And in order to get something out on C1, both A0 and B0 must be equal to 1. And we can make a truth table out of that, where we have A and B in, and we call it C out, which is the carry here, C1, and sigma is the S0. This is taken from an ordinary textbook. And you see here, if we start with sigma, which is S0, is different from 0 when you either have B equal to 1 or A equal to 1. Then you get sigma A XORed with B, and C out is equal to 1 when both A and B is equal to 1, and that is an AND function. And here you see the realization of it in electronics. Here you have an AND port, and here you have an XOR port, and here you have the sum out, and here you have the carry out. And here is A and B coming in. In fact, when we find diamonds like these in Claude Shannon's circuits, it's an XOR function. To the left, we have when we are adding digits different from the first digits. And here we have AJ, BJ, and CJ. If all of them are 1, you see that you get out CJ plus 1. And if AJ and BJ is equal to 1 and CJ is equal to 0, you also get out a 1. And if AJ is 0 and BJ is equal to 1 and CJ is equal to 1, you also get out CJ plus 1. And Sj you get when either Aj is equal to 1 and Bj and Cj are equal to 0, or when bj are equal to 1 and aj and cj are equal to 0, or cj are equal to 1 and aj and bj are equal to 0. And then if all aj, bj, and cj are equal to 1, you get first 1 here, 1 here, 1 here, and you also get something out on the sj. Claude Shannon made a simplified diagram of this where he removed the redundant parts here, and it's still the same, having a, j, or bj, or cj equal to 1 gives us sj, and if we have aj, bj, and cj equal to 1, we get sj, and cj plus 1 we get if we have either aj or bj equal to 1, or if we have aj, bj like this, that means aj equal to 1, bj 0, and cj equal to 1, we get cj plus 1. And if we have aj equal to 0 plus bj and cj equal to 1, then we get cj plus 1. And then we can see that this c out, which is the same as cg plus 1, what is that? Well, it's aj multiplied by bj. That is an AND function of a and b. And the other one, here is the diamond, and then it is an XOR function times cj, and that is what we get here. And on the sum part, that is the sj part, we have the diamond that we have here, and that is the XOR part. If that one is equal to 1 and this one is equal to 0, or this is equal to 0 and this is equal to 1, then we get something out on the sj. That means that, okay, we have XOR of a and b, and we XOR it with cj. We get all these things we have here. Here is when we have XOR of a and b, and then cj. And if we have down here, we don't have XOR of bj, but we get it when we get cj equal to 1, when we XOR aj, bj with cj. And the same thing is true when you are, well, let's see here, then we are, these two are 0 and cj are 1, we also get an sj. So the sj and the sigma can be written as a XOR'd with b, XOR'd with cj. And here is the truth table that is taken from a textbook, and we see that if all a, b, and c in is 0, we get nothing out. If c in is equal to if b is equal to 1, we get something out here on the sj. If both b and c is equal to 1, then we got something out on the cj plus 1, but nothing on the sigma. If a is equal to 1, we got something out on the sigma. If both a and c in is equal to 1, we got something out on the cj plus 1, but nothing out on the sj. And then if we have a and b equal to 1 and c equal to 0, then we got something out on the cj plus 1, but nothing on the sigma. And if we have all ones, we get both things coming out here on cj plus 1, plus on the sigma, which is the sj. And you see here, this thing here can be realized using two half adders. Now we have learned from Claude Shannon how to make a digital adding device. And here I've started with a half adder, and you see here, it's A, B in, no carry in, and we have carry out by anding A and B, and we get the sum out, the sigma out by X or A and B. Then we have the full adder, which is two half adders put together like this. And we have carry in, we have an A and a B. The A and the B goes into the first half adder, and out of the first half adder, the sigma goes into A on the next half adder, and the C out on the first half adder is ORed with the C out of the second half adder, and the carry in goes into the second half adder. And out we get the carry and also the sigma, the sum of the two half adders. So here is the full adder. And how to use it? Well, we just put a lot of adders here. Every one of these add 2 digits and take in a carry. We see here that the first one set the carry to 0. So then it acts like a half adder, and these are full adders. And I put them together like this. I take the carry out and put it into the next one, and then the carry out into the next one. And in this fashion here, this is the least significant bit. These are the most significant bits. And there are 4 bits added together. Here is A1, B1, A2, B2, A3, B3, and A4, B1. And you see here, most of them is set to 1 apart from that one, and it adds up to 1Z. Here I have constructed a 4-bit adder by making a hierarchical design of these 4 full adders. It has been a great journey to read Claude Shannon's master thesis. He has learned us how to add binary numbers, and he has also learned us Boolean algebra. Here are some of his references. Journal of Symbolic Logic has he been reading. He has also read the Algebra of Logic, Universal Algebra. He has read Mr. Huntington. He has also read George Boole's Finite Differences, and also the history of the theory of numbers. What have we been reading the last 30 minutes? Well, it's been Claude Shannon's master thesis, and I have also used multisim to recreate his great design.